So this is a, week 3 live session. So myself Sana Sheikh from IIT Bombay. I'm a second year PhD student, and I'm going to take a live session of NPTEL course Mechanism in Organic Chemistry on every Saturday from 3 to 5 p.m. Because of last week health issues, I have postponed the session for today. So the course instructor for this course is Nanita Madhavan from IIT Bombay. So in today's lecture, what we are going to do, we are going to focus on a rate law. So what is rate law, and how we can apply rate law for determining the proper mechanism, we will learn in this live session. So first of all, you should know how to derive the rate law. So here, as I am going to revise ma'am's slide, you can see here this is a simple reaction given here, A plus B. K observe is a rate constant which will give a product P. So there are different types of reaction, all of you know that. So first of all, we will start with the easiest reaction, that is called elementary reaction. Elementary reaction means a reaction which is a single step reaction, and in single step reaction like SN2 or other reactions are also there. So what happens in single step reaction, both the reactants participates together to get the product. So if we are talking about the elementary reaction, what will become a rate law? Rate law is actually the rate of the reaction is depends on the concentration of the substrate or reactant. So how we will write? We will write rate equal to rate proportional to concentration of reactant. How many reactant we have? 2. So A plus B. A plus B. Now we have to write the in equal form. That's why we have written here rate equal to K is a constant. Rate constant. K is called as a rate constant. So why the overall order of this reaction is 2? I hope all of you have already watched the video, but still I am revising all these things. So because this rate is depends on both the concentration A and B equally, so that's why the charge of the concentration will become 1 1, because it depends on both the reactant equally. That's why the order of reaction will become 2, 1 plus 1, or we are doing this way. 1 plus 1 will become 2. So order of reaction is 2 here. So this is a rate constant equation for elementary reaction. Now let's talk about the complex reaction. Complex reaction means what happening here. First we have our reactant A, then it's get converted to intermediate like SN1 reaction. Sorry. SN1 reaction. So what happen in SN1 reaction? First carbocation formation is taking place, then nucleophile attack takes place. So similarly here also we have reactant A first, then it undergo intermediate formation. Then after intermediate formation, it will react with reactant B, which is nucleophile also we can say nucleophile, which will give you a product. So this is a two-step reaction. Sorry. This is the two-step reaction. So, what will be the rate here? You have to write rate in two different ways. First, for intermediate, first overall reaction rate we have to write. Then we will compare the actual rate. So, with respect to P, rate equation will become the concentration of reactant. So with respect to P, you can see here intermediate I and B is are a substrate. I and B are the reactant for product here, and K2 is our rate constant. Always remember that whenever we are writing rate law, we first of all we are considering the product formation. So that's why in short we are writing here rate of product formation, which is rate equal to K2 is our rate constant, and concentration of I and B. Now we have to derive the actual rate equation for this one. So according to the steady state approximation, that means the state where we, according to the definition also, the steady state means here the transient state, transition state we can say, where intermediate is formed, is immediately consumed by the product. When as soon as it's formed, intermediate formation is takes place, immediately it gets consumed by the uh, product, consumed by the other reactant to converted into the product. So that means the formation rate of I is equal to consumption rate, because it's immediately get consumed. So according to the steady state approximation, formation rate will be equal to consumption rate, right? Always remember that steady state approximation is only for intermediates or highly reactive species, not for the reactant or a product, because intermediate is unstable, it has very high energy, so steady state approximation can apply on intermediate. So formation rate of intermediate is equal to consumption rate, right? So what will be the formation rate? Formation rate means it is a forward reaction K1, right? So it will become rate is equal to K1 into concentration of A, because we are talking about this forward direction. Formation of A is in forward direction. Sorry, right? So this is a formation of intermediate here. Then consumption rate. What will be the rate for consumption rate? Now you have to look in this direction. So according to this consumption rate, sorry, yeah, consumption rate, what will be the rate? Now here you can see that this intermediate is get consumed by this direction also and this direction also, right? Here also the consumption of intermediate is takes place, and it's going to back reaction also. That means here also intermediate is get converted to reactant. So here we have to write the consumption rate in both the terms. So first we will write here K inverse is rate constant here, and always we are writing reactant, right? The reaction is going from this direction here. So the I is our reactant here. In this case, intermediate is our reactant, because it's converting to the product A. That's why. So K inverse I will be our first rate with respect to this K inverse. Then the second rate equation will be based on K2. So then plus sign will be there, because we are adding both the rates, consumption rate. Then K2 is our rate constant, and again it will depends on reactant. So I plus B concentration will be our rate of consumption. So this is the equation for consumption rate. Then applying a steady state approximation, what we will do, we will compare both the equation here. So rate of formation equal to rate of consumption, right? Then we will take the intermediate I as a constant, as a common here. Then it will undergo bracket by simple max only. Then we will keep concentration of I on one side, and then this whole equation will go on denominator, and it will give this equation. Then after getting this equation, we are getting value of I. Then we will substitute this I value in the rate equation what we have written earlier, this one. So here substitution will take place, and we will observe that K2 will remain as it is here, K2. Then instead of I we will write this equation. So here it is K1 A and K inverse plus K2 B, and B is this B is coming from our equation only, right? These two things. So this is the rate equation after substitution of I value, intermediate value. Then if we will write in simplest form, we will observe that K1, K2 and concentration of A and B are divided by K inverse plus K2 concentration of B. So this is the rate equation for this type of reaction, that is SN1 reaction. I hope all of you understood this one. This is the SN2 reaction rate equation. Okay. Then again we are deriving the rate equation for other type of reaction. In this earlier case, here what we got, uh, reactant A undergoes some reaction to give the intermediate, then that intermediate is further reacted with other substrate or nucleophile to give the product, right? But here what happening, two different substrates are undergoing a reaction to give the intermediate, and that intermediate is directly gets converted to product without any addition of uh, substrate or nucleophile. So this is a different type of reaction. So how you will write rate equation? Again I told you, uh, always remember, write rate equation with respect to your product. So with respect to your product, rate equation will become K2, rate is equal to K2 and concentration of I, because you have to consider the first reaction, last reaction you can say, product formation reaction. So that's why the rate will become this, rate equal to K2 concentration of I. Then again, because here intermediate is present, we can apply the steady state approximation, and according to steady state approximation, rate of formation is equal to rate of consumption of intermediate. So again we have to write the formation and consumption rate. So in terms of rate of formation of intermediate, what you will write, K1 equation will be considered for writing the formation rate. So K1 will be your rate constant, then concentration of A and B will be there in rate equation, because these are substrates reactants concentration. So this is your formation rate. Then if in terms of consumption rate, we will write here first K inverse, because this direction I have already explained in previous example. Then this is our starting material or reactant, this is, so that's why K inverse I plus K2 I will be our consumption rate. Then after getting this equation, we will here we will consider I as a common, and it will become K minus 1 plus K2, right? This will be your equation. Then this K minus 1 plus K2 will go that side in denominator, and we will get this equation, that means the value of I. Then we will substitute the value of I in our rate equation, which we have written earlier, and then that means K rate equation will become equal to K2 K1 concentration of A concentration of B divided by concentration of K minus 1 plus K2. So as you can see here, in denominator there is no concentration of any species, not intermediate, not a product, and not even reactants. That means here only constant is there. There is no concentration of any species. That means we can write all the constant values as a K observe. K observe. So that's why K observe is written here. It will become, rate equation will become equal to K observe concentration of A and concentration of B. So here K observe is equal to K2 K1 divided by K inverse K minus plus minus 1 plus K2, this whole equation. Then here another reaction possibility is there. Actually we are covering different types of reactions here. Now in previous cases we are getting we had in this case two substrates, two reactants, and intermediate, then product formation. But here we are getting we have here one reactant, then it will convert it to intermediate, then product one formation will takes place along with the intermediate. Then this intermediate again undergoes will in a reaction with B reactant to give the product 2. To give the product, product 2. So for this type of reaction, how you will derive the rate equation? So here rate equal to K2 concentration of I. So always I have told you earlier also that that always write rate equation in terms of product formation. So for final product here is our P2. So we will write equation in terms of P2. So for P2 rate equation will become K2 concentration of I and concentration of B by considering this reaction. Then again we will apply the steady state approximation because the intermediate I is present here. So for formation of intermediate I, we will write equation K1 into concentration of A, which is equal to consumption of intermediate I, and we can write consumption equation as a K minus 1 here by considering this reaction K minus 1 concentration of I and concentration of P1 plus K2 concentration of I and concentration of B. If you are not getting any equation, please ask me that time only. It will be easy to understand now only. Later you will get confused. Okay. Then we will get from this equation, we will get the value of I. Then we will substitute this value in our rate equation. So rate equation will become K2 concentration of B, K1 concentration of A divided by K minus 1 concentration of P plus K2 concentration of B. So as you can see, we are writing all the constant together, K1 plus K2, and in denominator we have these two species also. That means we cannot write here as a K observe. So this is the rate equation for this type of reaction. This is the final rate equation. Okay. Now we have covered these all type of reactions, and what we observe that in all these type of reaction, the numerator is showing the, this is a simple SN2 reaction. So we are talking about other complicated reactions. So here numerator is always the formation of product. Formation of product. and numerator is the formation of product, and denominator is showing a consumption of product, or we can say it's a reverse case, consumption of substrate, right? You can compare here also, like in first equation I can say uh, product formation P will depends on concentration of reactant. Here we have reactant A and B, right? So this is the formation of product, and K1 K2 are rate constant. Here K inverse and K2 concentration of B is a reverse reaction, consumption of, or we can say reverse reaction means the consumption of intermediate, in terms of consumption of intermediate. So this is common in all these rate equation, right? Now distinguishing the between the mechanisms here, how we can find out? So here we have example. Now we were taking the A, B, these type of alphabet to represent the reactant and substrates and products. But here we are taking a organic reaction example. So here we have Rx. The X is any living group, and we have it reacted with a nucleophile to give the R and U, that is the product, like SN2 reaction only. So if we will write the rate equation for this type of reaction, what will be the rate law? Change in product formation with time, dp by dt, that means this is the product formation with time t, will depends on equal to k1 and concentration of Rx and nucleophile Nu. So this is our simple rate equation, and that's also called as a second order reaction, because rate is depend on both the substrate or reactant. While talking about the SN1 reaction, what happens in SN1 reaction? First, the carbocation formation is taking place. Then carbocation formation will give R plus here anion. Then X minus will leave. Then in second step, nucleophile will attack on carbocation to give the product. So this is a two-step reaction. So for this reaction, we will write rate law dp by dt equal to K1 K2 Rx and U, as we have already discussed this type of reaction here, correct? This equation. So just we are writing here in this form, last equation, right? I hope all of you understood this rate law. Then here, because whenever we are observing SN1 reaction, nucleophile we are taking always more reactive than the uh, other species for recombination of uh, carbocation and X minus. So always we are taking more reactive nucleophile for this type of reaction. So what will happen? If the rate of consumption of this carbocation will be very fast, rate of consumption, but the rate of formation of carbocation will be slow. That's why this is a rate determining step. So because rate of consumption is very fast, that's why we can ignore the uh, k minus 1 will be very negligible. So as all of you know that this is the first step, this is the second step. So as I told you, we are taking a more reactive nucleophile, that means this is the fastest reaction, right? Nucleophile attack will be the fastest step here. That means it will, K2 is much more greater than K minus 1, right? Because it's the fastest reaction. So that's why we can ignore K minus 1 here, and if it will become negligible, so this value will become 0. Then in denominator we have K2 and nucleophile concentration. Then K2 nucleophile concentration will get cancelled and we will get K1 and concentration of Rx. So what this equation suggests? This equation suggests that the SN1 reaction rate is independent of the uh, nucleophile concentration. It's not depend on the concentration of nucleophile, because the rate determining step is first step only, and here uh, nucleophile concentration is not mattering for giving the rate equation. So in terms of graph, if we'll talk, we will see here this x-axis is the concentration of nucleophile, y-axis is a dp by dt, that means the product formation with respect to time. So nucleophile concentration is not affecting the product formation here. Rate equation is independent on the concentration of nucleophile for SN1. Whereas in talking about SN2 reaction, here we can say nucleophile concentration is altering the rate of equation. So here we can see nucleophile concentration will affect the rate equation for second order reaction, SN2 reaction. Now let's talk about the E2 and E1 elimination reactions. So in E2, what happens? Leaving group elimination takes place, followed by the double bond formation, right? So this leaving group will leave, and here the double bond formation will take place, and here proton abstraction will take place by base. So this is a one step reaction. Now let's talk about the E1. First, listen here. In E2 elimination reaction, we have base and our substrate, right? And then product formation and our byproduct leaving group. So this is a type of SN2 reaction. That means we have, if we will write rate equation for this reaction E2, what will happen? We have to write the uh, this R. We are considering this group as a R and leaving group. This is whole moiety RLG. RLG. So rate will depends on concentration of RLG and K observed. We are taking here K observed, right? And concentration of B also, because base is also here. So this will become the rate equation for E2 elimination reaction. Now let's talk about the E1. So in E1 reaction, what happens? First carbocation formation is taking place by elimination of leaving group. Then base is attacking to abstract the proton, and it gets converted to double bond. So in first step here, in first step, this is a rate determining step. Step means slow step. So here we don't have base in starting equation as a reactant. In second step, we are adding a base, right? So for in terms of rate equation, what we will do here, we will write K observe here. As I always told you, rate determining step will affect the rate equation. First step is the slowest step, that's why it's a rate determining step. So K observe is equal to, rate is equal to K observe, and this RLG group means our starting material. It doesn't depends on a other substrate present in the second step reaction, because in case of SN1 also we observe the same thing. So the even elimination is same as a SN1. The difference is that only that reaction is substitution, and this is a elimination reaction. So again, here we can say rate of even elimination reaction is doesn't depends on the base of base present in the reaction. Sorry, base. There we said nucleophile. Here we can say base. Right. So this is the rate equation for even elimination reaction. Now you can see the graph again. This is E2 elimination reaction graph, which is similar to SN2 here, right? And this is even graph we have not drawn here. It will also look like SN1 reaction, this one straight line. That means there is no dependency of base concentration. Now here we have example of different type of reaction. So this is not a SN1, not SN2 reaction. This is a different type of reaction. So here we have thiamine. So all of you see here we have leaving group, this whole group as a leaving group, correct? So how the reaction is proceeded? First SO3 2 minus will attack on acidic carbon, sorry, more reactive carbon. So which one will be the more reactive one? So here you can see this carbon is next to nitrogen, and it is more acidic compared to the other, uh, compared to this position, this carbon. So what will happen here? SO3 2 minus will attack on this carbon, right? So SO3 minus attacks will takes place here, and this double bond will get break to give the intermediate, this like this one. And then after getting this intermediate, the lone pair of nitrogen will push here, and this double bond will shift here, and leaving group will eliminate it, Lg, and it will give double bond over here. Then SO3 2 minus will attack on this double bond, and it will again get tautomerized to give the substrate intermediate here. And again we have a lone pair on nitrogen, so lone pair will push here, and this SO3 minus will eliminated to give the corresponding product. So this is the product here, and we can see here we are using here SO3 2 minus 2 times. That means it is the order of SO3 with order of reaction with respect to SO3 2 minus is 2, right? Second order with respect to SO3 minus concentration, correct? And with respect to or substrate, I am writing here R is first order reaction only, because only one single concentration is participating in a reaction. And sorry, here I have written sign will not be there, sorry for mistake. Okay. So this is the order of the reaction. So 2 plus 1 will become 3. So this is a, sorry, this is a third order reaction, not first order, not second order, it's a third order reaction. Okay. Then again we are going to talk about the kinetics study of reaction mechanism. So how to study kinetics? So we have to with kinetics we should understand the change in concentration of the reactant over time with the formation of product, right? So reaction lifetime is in the range of minutes to hours, depends on reaction to reaction. So when reaction is going, we are observing the reaction continuously by different techniques. So here some techniques are given: use of NMR, fluorescence, UV visible, HPLC or IR, to monitor the intermediate formed during the reaction. So and apart from these techniques, use of an internal standard also helps to monitor the conversion. So what happens in NMR? We are taking in this technique, when the reaction is going, we take some amount of reaction and record the NMR, which can give the uh, product and intermediate formation. It is also done by in situ IR and UV visible spectroscopy also. So how the reaction is going simultaneously, the IR is recorded to observe the change in uh, reactant concentration and product concentration. And the other method, which is internal standard, also helps by adding some amount of internal standard which remain unreactive during the reaction, but it will give the relative value in a NMR to find out the concentration of product. We will discuss this also. So first understand internal standard. So we suppose we have reaction here, COET, right? Ethyl acetate. Then it will undergo titration to give the acetic acid, and this acetic acid will formation will take place along with the ethanol, right? Then this if we will observe the formation of acetic acid and ethanol, we did not observe the UV activity. So UV visible spectroscopy we cannot use here, but when any conjugation system will be there, then it will give a UV activity. So here in the similar case, you can see here we have benzene ring, which have aromatic ring here, which will give the UV activity. So we can observe with UV active spectroscopy this product formation. So we can add internal standard uh, in this type of reaction, which is known molecule and known concentration. Known molecule, known concentration is used as a standard internal standard. So here we can see NMR spectra. Suppose we have this NMR spectra value from 0 to 7, proton spectra 1H, 1H NMR spectra, and we are getting some known compounds which we have used as an internal standard. As I told you, known compound with known concentration should be used as an internal standard. So we have here internal standard, and we have integrated the proton here. So suppose we have internal standard here 2 proton, right? We know we have 2 proton here in standard. Here we have using here tetrachloroethane as a internal standard. So here we have 2 proton. 2 proton means we will integrate this peak value as a 2. Then with respect to this one, we will observe our product's value, proton value. So suppose we have complicated structure, we are getting different peaks in different region, here also and here, right? But we should find out the uh, some characteristic peak, or we can easily find out in the product. So here we can see, if a oxygen, next to oxygen we have one carbon atom which is having 2 proton, right? So you all of you know that next to oxygen 2 proton will give the uh, P, and a value between the 3 to 4 ppm in proton NMR spectra, right? So all of you should have rough idea about this value. So you know, in this region we are getting one peak which is integrated as 1. That means it is giving a representing this proton, right? So we can compare now this proton with this one. Sorry, this one. So we can say 2 proton is equal to 2, which is showing 1 proton, right? And if we are talking about here integration, it is giving 1 proton, but we know that we have this is as a 2 proton, right? So with respect to internal standard, we can say 1 is equal to 2 proton. That means 1 proton is equal to 0.5. Sorry, here it is given 2 proton, right? 2 proton, and here we are getting 1, but actually we know that we have 2 proton, correct? By structure, our structure. So if 2 proton is equal to 1, 1, that means 1 proton is equal to 0.5, right? 0.5. So x millimole of TCS if present, if 2 millimole suppose is present, that means 2 by 2 millimole of substrate present or product, right? So this is a relative value we are finding with the use of internal standard. Now determining the nature of intermediate. So there are different types of intermediates: carbocation, carbanion, radical, carbene, right? Different types of intermediates, and these are in resonance also. So you can also understand this structure we have already discussed in previous classes. So Hammett equation we will talk about in this session. So Hammett have considered the simple reaction to find out the Hammett constant and equation. So here he has used the benzoic acid, and which gives the uh, corresponding anion with H plus ion. So according to the Hammett, he has considered the benzoic acid as a simple reaction, but present on of presence of any substituent on this benzene ring will affect the equilibration or not. So this has done by some studies. This equation have proved by some studies. Here we are going to discuss. So we are talking about effect of substituent on equilibration. So suppose we have X at para position. This is ortho position. I hope all of you are aware of this one. Ortho, meta and para. Right? So at para position we have different substituents like OMe, H and NO2. So we have to arrange the K value in increasing order of magnitude. Means the equilibration, change in equilibration. We will talk about in detail. So when here OMe will be present, so what happens? This lone pair of OMe will push here and double bond will get shifted to this position, and this double bond will again shifted here and negative charge will generate over here. So as you can see, this negative charge is not stabilizing the structure, and it's destabilizing this structure by creating two negative charges. Here while talking about the NO2, it's giving a resonance, right? This double bond will shift here, and double bond formation will takes place between nitrogen and carbon, and again this bond will get break. So here you can say carbocation formation is taking place at this position, and this is stabilizing the structure. Electron withdrawing group NO2 is there, and which is stabilizing the structure. That means it will the equilibration will be more at the right side, shifted more towards the right side, right? This so the right side will be more stable. That's why it's stabilizing the reaction. Whereas in case of electron with really sorry elect, electron rich group, the equilibrium will shift from on this side, and in case of H, it will remain as it is. Correct. So this is a trend. K value change for K when the substituent NO2 is present, the K will be higher, and KOMe will be lowest in this case. Correct. Because it's giving a equilibration more inclined towards the forward reaction type, right side, and in OMe case it's destabilizing. That's why KOMe will be lowest one. So this is a trend. So this is a Hammett standard reaction and substituent effect. So according to Hammett standard equation, log kx divided by kh is equal to sigma x. This is called a substituent parameter or a substituent constant. So as I told you, x equal to OMe, so that means it is destabilizing the molecule. So it will be lowest. K value for this reactant will be lowest when x equal to OMe, right? So Kx is less than Kh. So when Kx is less than Kh, the value will log Kx by Kh will become less than 0. Correct? So value will become less than 0. When x is equal to h, it will become log 1, which is 0, and the reverse case, when kx is greater than kh, will give the value sigma x value greater than 0. So whenever the sigma x value is more than 0, that means electron withdrawing group is present, and whenever it is less than 0, that means it is a destabilized form and electron rich group is present. So this is a comparison for sigma values. As you can see, NH2 is donating, is giving a plus M effect, so it's giving a minus 0.66 sigma value. That means it is destabilizing the molecule, and you can see the relative number here. You don't have to remember all the numbers here, but you should have a relative idea only. So in case of OH, it gets increases. In case of OMe also, it's destabilized, but compared to NH2, it is slightly on stabilized side. And here you can see in methyl case also, we have minus value only 0.14, but when the phenyl group is present, the value is slightly we can say equal to 0, approximately equal to 0. That means because H is present, instead of X, it is a phenyl group, so H is similar to H, it will give a value. And in case of fluorine, bromine, iodine, because these species are giving a minus I effect as well as plus M effect, that's why the value is not constant, it's different. depending on the reaction. Now let's talk about the other substituent. Here we have COCH3. It's giving a because it's a more electron withdrawing compared to the acidic group, carboxylic acid group. That's why it will give a 0.47 sigma value. And here you can see this OCOCH3 carbonate is less electron withdrawing compared to the acidic group. That's why it's giving a 0.31 sigma value. And similarly you can compare others value also. CF3 is more electron withdrawing compared to all others above species. That's why it's giving a 0.53 sigma value. And cyano group is also highly electron withdrawing group, so you can see the value. So I hope all of you understood the relative value for the substituent present on the para position. So, sorry, sorry, I didn't get. Actually, it depends on the reaction. Sometimes it's minus I and sometimes it's plus M. That's why the value is not constant at para position. You can see here for F minus, here we have 0.15, and in case of chlorine, bromine and iodine the trend is not followed. So depends on reaction. Sometimes minus M, sometimes plus M. Okay. So we have talked about the para position. Now we are talking about meta position. So in meta position, as you can see in meta position, the lone pair will push here and negative charge will generate at ortho position, right? Which is also destabilized only. So we can see here in terms of meta position, but not as compared to the destabilization is there, but not compared to the para position. Para position uh, was more destabilized. That's why the value at meta position is slightly greater than compared to the para position, right? Slightly greater, or we can say greater than the para position value but less than 0 only. And in case of OH, OMe also you can observe the same trend, whereas in case of these other type of substituent, acid, carbonates and cyano nitro group, we will observe here the stabilization at para position is more compared to the meta position. So substituent present on meta positions are more stabilizing the molecule compared to the meta position, as values are different. Here you can compare the values, right? Now here are some points to remember for the Hammett equation. So as all of you know that benzoic acid deprotonation is a standard reaction taken by Hammett for substituent parameter sigma. So benzoic acid deprotonation is a standard reaction, and by changing the substituent present on this benzene ring will give the different value, which is already done, and these values are available in different books also. So you don't have to do the reaction, and just values are there. So according to the Hammett equation, log kx by kh equal to sigma x, right? We have already discussed. And if sigma x is greater than 0, that means electron withdrawing group is there, and if sigma x is less than 0, that means electron releasing groups are there. So the effect at para position is more compared to meta position. I have already discussed here. You can compare the value. So effect at para position is more than meta position. Now using a sigma value to understand the mechanism here. So as we according to Hammett equation, we have taken the benzoic acid reaction as a standard reaction, right? So equation Hammett equation will become this log kx by kh equal to rho sigma x. What is rho here? So rho is a reaction constant, we can say, or reaction parameter in Hammett equation. So what is Hammett equation? All of you know that log kx by kh, right? This is a substrate. This x is representing our substrate, which is equal to rho log kx by kh. So this e e equation, this Hammett equation is for benzoic acid, because we are using benzoic acid as a standard. So this is for benzoic acid. So this will remain same everywhere. So this equation is also called a linear free energy relationship. We will see here in detail linear free energy relationship. Why it is called linear free energy relationship? So here you can see we have our equation, Hammett equation, log kx by kh equal to rho sigma x, and we also know that delta G is equal to minus RT ln K, natural log K, right? So we can write in this form also, minus 2.303 RT log K, right? And now we will substitute the value of G, value of K in log K in our reaction. So first of all, we can write this equation in different form also, simple mathematics only. So log kx by kh can be written as log kx minus log kh, which is equal to rho, and again we can write this equation in minus form, right? This way for benzoic acid. This is for benzoic acid, correct? Then now we will substitute the value of log k. If what will be the value of log k? Delta G divided by minus 2.303 RT. This value will go that side on denominator, right? So instead of kx, we will write here delta gx divided by 2.303 RT, and then minus sign will be there, and minus sign from the equation will also come, which will become plus. Minus minus will become plus, and we will write here delta gh divided by 2.303 RT, and same we will write that side also. Now all of you can see here we have constant term both the side, 2.303 RT, which will get cancelled to give the minus delta Gx minus delta H whole bracket is equal to minus rho and delta Gx minus delta H of benzoic acid. All of you understood this equation? Now because now because this is the difference of delta G energy, so delta is representing a difference, and difference of delta G, that's why we are writing here delta G R is equal to rho delta G benzoic acid. This minus sign will get cancelled both the sides. So this is the equation for linear free energy relation. So this equation is giving a linear free energy relation. That's why it's called a linear free energy relation. I hope all of you understood this equation. So now let's talk about the Hammett plots. So suppose some reaction is going on this substrate, and we are getting here benzoic acid along with some substituent plus alcohol, right? So for this reaction, substituent X will vary. Here we have different types of substituent, that is amine, nitro, methoxy, chlorine and methyl, chloride and methyl, correct? So you have to find out the different position of this substituent. We will discuss here. So when how the reaction is taking place, this nucleophile will attack on carbonyl carbon, and the bond between carbon and oxygen will get break, and minus charge uh, will be carried by oxygen atom. So this is a negatively charged species, right? Now, if substituent will be different, like in case of NH2, what will happen? We have discussed earlier. It will give electron rich uh, group, electron releasing group, right? And this is the electron withdrawing group. So always remember, electron withdrawing group will give a high stabilization compared to the electron with releasing group. Okay. So here we have graph where on x-axis we have log kx by kh of benzoic acid, and on y-axis we have log kx by kh of our substrate, and this slope is our rho value is our slope. So all of you remember the equation. The Hammett equation was log kx by kh equal to rho log kx by kh of benzoic acid, right? So here we have all the terms. Now this is our slope. So as I told you, log kx by kh will remain as it is, only rho value will change. So rho value for NO2 minus will be higher here. Why it will be higher and positive? Here rho is positive, right? So electron withdrawing group is stabilizing and electron releasing group is destabilized. So rho is positive and it's giving a high value for NO2 because it's the most electron withdrawing group. So here the Kx is greater than the Kh, right? Kx is greater than 0, as I told you. In earlier case we have discussed that when electron withdrawing group is present, that means Kx is greater than 0, right? And all of you know that when Kx is greater than 0, that means it's greater than Kh. So this is the value for NO2. That's why it will give highest value here. It's greater than 0. Now let's talk about the chloride. Chlorine is also an electron withdrawing group. As I told you, it can show plus I and minus I and plus M effect. That's why it's less electronegative or electron withdrawing compared to the nitro group. So that's why this it will give here value, and again here because the value will remain positive only with both the effects. You can see in this table here for minus Cl, for chloride ion X, if chloride ion is there, the value will always be greater than 0. Always be greater than 0, right? In both the cases, greater than 0. So in this graph also it will remain greater than 0 only. So in this case rho is positive and Kx is greater than Kh. So it's stabilizing the molecule. Now in case of Me and OMe, all of you know that these two are electron uh, rich group, electron releasing group, and NH2 also. So these will give the value below 0. You can see here 0 is there, and these are showing a value less than 0. So Kx is less than 0 for this one, this species, and it will give a equation this one Kx is less than Kh. So I hope all of you understood this graph also, Hammett plot. So here we have discussing about the significance of rho. So here all of you know that this straight line, this dotted line is showing the rho value for slope 1. Here you can see this is a standard value. But when the this slope is slightly tilted this side, that because of presence of ethanol in the reaction. Presence of ethanol will change the slope slightly positive side. But while talking about this slope, it is a on negative side. So all of you know that here P1 is greater than P2, right? So if sorry, rho 1 is greater than rho 2. So if rho 1 is greater than 1, this is greater than 1. This is value for 1, and this side is greater and this side is less lesser. So when the rho is greater than the benzoic acid rho, that means the reaction is more sensitive and it is more reactive. But when the rho value is decreases compared to the benzoic acid, that means the reaction is less sensitive compared to the benzoic acid, right? And if rho is equal to 0, that means reaction has no substrate effect. 0 will look like this one, straight line. So it's slightly greater, that means it slightly depends on the substrate effect. So here we have discussed the ma'am's lecture from week 3, that is class number 10, 11, 12, 13, 14. Now we will do some questions based on these lectures, which will help you to solve the assignment questions. Now the first question is, for the given reaction, which statement is correct when the concentration of alkyl bromide is double? So you can see both the reactions here, reaction A and reaction B. So first of all, you please think about this reaction, this question. If you are getting answer, then it will be fantastic. Otherwise, I will explain all. Yes. Third, C. Why is this so? Huh. Right. But here you can please read the question again. When the concentration of alkyl bromide is double, think about it. So here, if you will see this, you are right. This is SN2 reaction, and this is SN1 reaction. But while talking about the rate, we have observed that rate of SN2 reaction is depends on both substrate plus nucleophile, right? So when you are increasing the substrate concentration, you are doing making it double. That means rate will become double, right? But in case of SN1 reaction, the rate is independent of concentration of nucleophile. So the concentration of nucleophile will increases, that means it will not affect the reaction rate. But if the it depend on substrate, but so when the substrate concentration is become double, it will affect the reaction. So if we will change the question, like uh, concentration of, instead of alkyl bromide, suppose we are writing OH minus is double, then your answer will be C, third one, for in terms of nucleophile, because nucleophile will concentration of nucleophile will not affect the SN1 reaction, but it will affect the SN2 reaction. So SN2 reaction rate will become double, and reaction B rate will become unaffected in terms of OH minus concentration. but here the question is different. So please understand the question carefully before writing any answer. People have made mistake in hurry. So remember, here we are talking about rate of uh, I will write rate law first. Sorry, rate will be depends on or alkyl bromide, right? This is rate equation for SN1, and here rate equation will be K observe I'm writing alkyl bromide as RBr as well as OH minus, right? So here also, if you are increasing the concentration of RBr and here also alkyl bromide, both will change the rate of reaction. So the correct answer is rate is double for both the reactions. All of you got it? I hope all of you understood. So it's depend. Your answer will be always depend on the question. If instead of alkyl bromide OH minus was given here, then the answer will become third one. But here alkyl bromide concentration is given. That means both the rate will change here. Okay. Now next question. For the reaction given by equation, the rate law is. So you have to find out the rate law here. So I hope all of you understood. Just now only we have discussed the rate law. So how we are writing rate in terms of product, right? Always write rate in terms of product. So here what will be the rate? K2 and intermediate I, right? This is our rate equation. Now we will find out the value of I by steady state approximation. Applying steady state approximation, what will happen? Rate of formation of I is equal to rate of consumption of I. So rate of formation is what? Concentration of A, concentration of B and K1, sorry, here, right? This is formation rate for I. Then consumption rate. Consumption rate will be K inverse, K minus 1, or you can say concentration of I plus K2 concentration of I, right? Now you will take I constant and this K minus 1 plus K2 will come in denominator. So K1 A B divided by K minus 1 plus K2, right, is equal to I. We will substitute this I value and our rate will become K2, K1, A, B divided by K minus 1 plus K2. So which is the correct equation? This one, right? So you can solve by these simple steps and you will get the correct answer here. All of you understood this question? Okay. So this is the another question. The Hammett substituent constant rho is based on. What is the correct answer? This is a theory question. As all of you know that. Sorry. Yeah, please answer. Yes, option 1. It depends on the dissociation of benzoic acid. Benzoic acid used as a standard. So, so here we have done three examples questions based on this topic. So for today's lecture we have covered the Hammett till the Hammett equation, right? So I will give the brief summary for today's session, and if you have any question doubt you can ask between this session only, this summary. So what we have done today, we have done the deriving the rate law. Here we have learned the different types of reaction rate equation, like for elementary reaction, which is SN2 reaction, we observe that rate is equal to K observed and concentration of A and concentration of B, which is a second order reaction and bimolecular reaction, because both the molecule is participating in the reaction and affecting the rate of the equation. For complex reaction, we have observed that we have taken the example of SN1, and we have observed that the intermediate formation is taking place, which is further undergoing a reaction with B to give the product P. So the rate is depends on the formation of product, which is equal to K2 and concentration of I and concentration of B. So we from this equation, because I is a intermediate concentration, sorry, so I is the intermediate concentration. So we have to find out the value of I. So according to the steady state approximation, we have observed that the formation rate is equal to consumption rate. That means as soon as intermediate is formed, is get consumed by the other substrate to form the product, or it get back converted to the substrate A. So that's why the formation rate is equal to the consumption rate. So we have applied the both the rate equation here, and we have observed that formation rate is K1 concentration of A, and consumption rate is K minus 1 concentration of I plus K2 concentration of I and concentration of B. So according to this equation, we have with this help of this equation we have find out the concentration of I, and we have substituted this value in our rate of equation, rate rate equation, and we observe that we are getting K1 K2 concentration of A concentration of B divided by K minus 1 plus K2 and concentration of B as our rate equation. Then we have observed the another possibility of reaction also, which is A plus B, which is giving intermediate I and which further converted to P. So A plus according to this reaction we have written the rate equation K2 and intermediate I. Then by applying the steady state approximation we observe that we get the value of I, and which is substituted in the rate equation to give the corresponding rate equation. But here we observe that the in denominator we have the constant value only. There is no concentration of any species. That's why we can write here as K2 K1 by K minus 1 plus K2 as a K observed, right? Then we have go through with the another possibility of the reaction also, where we have seen that A is getting converted to intermediate I and some amount of product 1 along, then intermediate is further get reaction with the substrate B to give the product 2. So for this type of reaction again we have derived the rate in terms of product 2 formation. So we have written here K2 concentration of I and concentration of B. As all of you know that we have to find out the concentration of I value by steady state approximation. Here we applied that steady state approximation, which is rate of formation of intermediate equal to consumption of intermediate. So from this equation we have found out the concentration of I, which is get substituted in the rate equation, and we have got the rate equation as a K1 K2 concentration of A concentration of B divided by K minus 1 concentration of P plus K2 concentration of B. Then here we have written all the reaction in one series, and we observe that uh, rate of reaction is depends on a formation of product. Numerator is always representing the formation of product, whereas the denominator is showing the consumption of intermediate. Then we have observed the actual reaction type. Instead of writing A and B, we observe that in SN2 reaction we have a RS, where X is a living group plus nucleophile, which is giving R and U. So here we have written the rate law, that is dP by dt, that means product formation with respect to time. So the reaction rate is depends on the concentration of both the substrate, that is nucleophile, as well as our uh, alkyl halide. Al yeah, alkyl halide. And when in case of SN1 we observe that the first step is a carbocation formation, then that carbocation will further undergo reaction with nucleophile to give the R nucleophile, R and U. So the first step here is the rate determining step, which is the slowest step. So that's why we will write here rate equation depends on the rate determining step. So as we have already discussed in the previous rate equation, sorry, here, right? This is the SN1 reaction. So the same equation we will write here also. So we have written here, and because this type of reaction is undergone a nucleophilic attack. So whenever we are doing this type of reaction, we are taking the nucleophile more reactive compared to the substrate. So more reactive nucleophile will be used. That means it will trap our carbocation very fast. That means this reaction is very fast. Fast reaction means K2 is very high compared to the K inverse, right? K inverse means it's getting back to its starting material. But here the product formation will be faster compared to the back conversion. That's why K2 will be higher compared to the K minus 1. So that's why we can here say K minus 1 is negligible and K2 is larger, right? So because it become negligible, so it multiply by X will become 0 only. So we will not consider this term, and we will observe here this equation. By cancellation of K2 and nucleophile, we will observe that rate equation is depend on K1 Rx, right? That means it independent of nucleophile concentration. So from this graph we can see that nucleophile concentration is not affecting the rate of SN1 reaction, while in case of SN2 it's depend on nucleophile concentration, right? Then we have observed that the E1 and E2 elimination reaction, and we have seen here leaving group elimination is taking place, followed by the proton abstraction by base, and which is giving here double bond. So but this is a one step reaction, so the rate will become uh, like SN2 reaction only, and it will depend on both the substrate or reactant in a reaction. So the rate for elimination reaction E2 will become K observe R LG and for even elimination reaction, as the first step is a rate determining step, then the second step is faster. So that's why the first step only will give the rate. So it depends on only the concentration of substrate or reactant, same as a SN1 reaction. So we have observed the graph also here. It's showing E2 elimination reaction showing a graph same like SN2, and E1 will show the graph same like SN1, which is showing no dependence of nucleophile concentration. Then we have observed the other order of reaction also. This is the third order of reaction where because the two molecule of SO3 minus 2 is participating in the reaction, that means the concentration of SO3 minus 2 is double. So first SO3 minus 2 will attack on this carbon atom, which will give the intermediate this like this, and then lone pair of electron will push here, and it will give intermediate here with elimination of leaving group, right? Then after elimination, SO3 minus will attack on the double bond again, and it will give the uh, di-substituted SO3 intermediate. Then a lone pair of nitrogen will push here, and it will get eliminated to give the desired product. So reaction order with respect to SO3 minus is second order, but overall reaction rate is third order reaction. Okay. Then we have done the how to study the kinetics. So there are different methods: NMR, fluorescence, UV visible, HPLC, IR, etc. to monitor the reaction, and there are internal standard method also there to find out the reaction. So we have discussed the how internal standard helps to find out the concentration of the product. So by integration we can find out the concentration of product with known protons, with some known protons. We cannot find out all the protons because sometimes we have complicated structure, but some known protons should be analyzed by comparing with the internal standard. Then we have done the different types of intermediate, which is carbocation, carbanion, radical, carbene. So Hammett equation have considered the benzoic acid as a simple reaction. So but substituent present on benzoic acid will affect the equilibration, which is given by the Hammett. So here the K value is given. So when the electron releasing group will be there, that time the K value will become less. That means it will destabilize the structure. But when the electron withdrawing group will be there, it will stabilize the structure and K value will become greater. And that means the equilibrium will shift towards the right side in case of the electron withdrawing group. And it will shift towards the left side in case of electron releasing group. Then we have observed the values here, log values, which is Hammett equation. Log kx by kh is equal to sigma x. So in case of OMe substituent, kx is less than kh, because we have observed here the value of k OMe is less than kh, right? Same here also. So when the kx will become less, the log value will become less than 0. So sigma x value will become less than 0. In case of h, it will become 0 because log 1 is equal to 0. And in case of the NO2 group, it will become more than 0. So this is the comparison of sigma values. As you can see, most of the electron withdrawing group have a positive sigma value. That means it is a more than 0. We have discussed earlier. So because of the positive and positive mesomeric effect and minus I effect, these values are not same. It's keep on changing. Then we have observed carbonates, as carboxylic acid cyano group relation also, and we have observed more electron withdrawing is giving a more positive value. Then we have compared the para value with sigma meta value. So here we observe that the meta effect is less compared to the para effect. In all the values, if you will compare, you will observe that the meta effect is less compared to the para effect, right? So in other words, we can say the effect at para position is more than the meta position. So this is again the revision of which we have discussed earlier. So sigma x is greater than 0, that means x is the electron withdrawing group. Sigma x is less than 0, that means x is the electron releasing group, right? Then we have done the Hammett equation, where we have log kx by kh equal to rho sigma x, and Hammett equation is this one only, because this sigma x is for benzoic acid, and this raw value is the slope of graph, and this is the substrate value, right? So it is also called as a linear free energy relationship, and we have discussed why it is called as a linear free energy relationship, because in terms of free energy, linear free energy, we have derived the equation. So I'm not going to again derive the whole equation. You can watch the recording which will be available on YouTube. So the final equation we got, delta G R is equal to rho delta G benzoic acid, right? Then we have discussed the Hammett plot. In Hammett plot, we observe that the highest this slope is a raw value, and on x-axis we have the log kx by kh for benzoic acid, that is sigma, and on y-axis we have a log kx by kh of substrate. Then we observe that here this is our 0, and at 0 we have x substituent as a h, and when electron withdrawing, we are observing electron withdrawing group, NO2 is the most electron withdrawing group, which is giving a more positive value of kx compared to the kh. So here kx is greater than 0, which is giving a kx greater than kh. That means rho is positive in this case. It is stabilizing the molecule. Now talking about the chloride ion, because as I told you, you can see that chart. In that chart, chloride ion will always give the positive rho value. Positive rho value. So that's why it will give slightly greater than 0, not compared to the nitro group, but it will be more than 0 only. That's why the here also we will observe the rho is positive. Then talking about the methyl and methoxy and amine group, we will observe these are giving a Kx less than Kh, which is less than 0. So here you can see the NH2OMe and methyl group in table also, they are giving a rho value negative. Okay. Then we have discussed the significance of rho. So the slope of the plot is called as rho, as I told you earlier. If the rho value is greater than 1, this dotted line is showing the 1 value, and above side is showing the greater value, and below side is showing the lowest value. So if greater than 1 is there, rho value is greater than 1, then that means the reaction is more sensitive than the benzoic acid. And if the rho value is less than 1, that means reaction is less sensitive than the benzoic acid. So if raw value is 0, like straight line, that means reaction has no substrate effect. Then we have done some questions. So here the first question was there for the given reactions, which statement is correct when the concentration of alkyl bromide is doubled. So here the concentration of alkyl bromide, that means substrate, which affects the rate of reaction in both the cases, SN1 and SN2 also. SN1 reaction is independent of concentration of nucleophile, but alkyl halide will affect the rate of reaction. So that's why rate will become double for both the reaction. The option 1 is correct one. Then we have discussed the reaction rate law equation. For given reaction, the rate law equation, we have found out the rate is equal to K2 and concentration of I in I have already told you, whenever you are getting any reaction, please write in rate equation in terms of product first, then you have to substitute the value of I by steady state approximation. So I have done the derivation, and we observe that the rate equation is equal to K2 K1 AB divided by K minus 1 plus K2, which is option number 3. Okay, correct option is 3. Then we have done the Hammett substituent. The Hammett substituent constant sigma is based on which parameter? So all of you know that Hammett substitution constant sigma is based on the standard reaction benzoic acid. So the dissociation of benzoic acid is the correct answer. One. That's all for the today's session. So I hope all of you understood everything which we have discussed in this lecture. If you have any doubt, any question, you can ask me in next session also or today also. Thank you so much for your kind attention. Any question? Thank you so much. Thank you. Thank you all of you.